They said something about like they're not allowed to have
Okay, and so this is what it looks like, and I'm going to show just a little video on how this thing works.
Those 26 contacts. But in the middle of this object, it's like spaghetti. So an A will go in at 12 o'clock, but it might come out as an F. It will go in here as an F, it might come out as a G or so. So the scrambled wiring inside these rotors is what leads to the encryption. But on its own, that's not enough. Scrambling is okay. Scrambling is simple. We can scramble without needing a machine. What the Enigma allows us to do is just set it up in a certain way. Let's set up here 21, 16, there we go, 11. So I do that same process again. I hit P 3 times. I hit the P first time, the lamp lights up, but also you'll see that that rotor moves. If that rotor moves, then the wiring goes in at a different junction. If it goes in at a different junction, it follows a different electrical path. If I type P again, you'll see the lamp light up, different lamp, but also the rotor will move. There we go. And it's this dynamism in the rotors that gives you the complicated encryption.
Okay, so you get the idea that this machine would type in England, or sorry, in Germany, the instructions to the U-boats. They would get sent out. You would know what the letters were. You could hear them because they were on shortwave, but they were in code, and you basically had to reverse engineer because they had these machines. They knew what they were. But they had to know the dial settings, and since the dials change after every character that you press, it was an incredibly difficult thing to decode. And here's one in use. You can see so this person's listening. Here's the Morse code operator writing down the characters, and here's the person actually typing them in, and this guy's reading the lights as they come up. So they're actually sort of figuring out what's going on. So here we are in Bletchley Park, where a group of mathematicians, including Alan Turing, went to actually figure out how to decode all these things. So here was a picture of the German U-boats that were around and trying to sink all the ships that were coming to supply England. So these are notes to myself, just to give you a sense. Turing figured out a way to decode the traffic that was coming in through the Enigma machine using a mechanical device, which he built, or designed and had built. It was called the bomb, and it would run through every dial setting of the Enigma machine until stuff came out that you could read. Before he did that, it would take about 3 weeks for them to decode the settings. And they were losing about 200,000 tons of ships every month. And what I just realized in my research is they only had 13 million tons of ships available. So losing 200,000 tons a month was not a good thing. When he did his thing and the bomb got going, they got it down to 1 or 2 days. And all of a sudden the tons of ships sunk went down to below 100,000 tons a month. This is one of the major reasons that people say Turing essentially saved England. If he had not figured this out, that they would have had to surrender because they would have been starved. And that's just brutally fast detail. There's some other stuff as well. This was one of the things Turing figured out. Here's a long German phrase that was in a lot of the transmissions. So they used the trick that in the Enigma machine, if you press the letter A, it would never go through the wiring and come out as A. It would never repeat itself. And they used that. So they would move this word they knew was somewhere in the transmission along, and if at any spot there was a repeating letter, they knew that wasn't the correct setting, so they would move it along again. And this was their kind of quick way to try and figure out possible settings. So that was the kind of thing they did. These were the rooms full of women who would sit and try every setting of the Enigma machine looking for something that worked. And these were some of the decoding tools that the mathematicians were using to try and figure out the settings for a particular day. The deal was every day the Germans would change the dial settings that they were starting at. So the key was to figure out the dial settings for a particular day so you could decode all that stuff. So you can tell if there's a book of dial settings, it would be really good to get that. And that's this next thing. These three people. The idea was the Navy knew that if they ever captured a U-boat, they wanted to get into it quickly and see if they could get the book of dial settings. U-559 was, it was about to be sunk. The Germans came to the surface to get out. Three people, Colin Grazier, Anthony Fasten, and 16-year-old Tommy Brown, who was on the destroyer working in the cafeteria. They dove in the water, went to the submarine, went down, got the books. Grazier and Fasten passed it up to Tommy Brown, who swam back to the boat, and Fraser and Fasten went down with the submarine. To me, that just blows me away. Yeah. So, and they claim, based on what they found, they shortened the war by a year. And they calculated, basically, about 7 million people were being killed a year in World War II. So these guys saved, in theory, 7 million people. This is Bletchley Park Hut 8. This is where Turing did his work. You can walk through that and see his stuff. Here is the bomb. And you can see that each of these collections of 3 dials essentially runs like a little mini Enigma machine. Here's a reconstructed one, and this is in the movie that's just about to come out. So that's the one thing. Now, there was another coding system that Hitler used to talk to his generals. It was called the Lorenz system. It was much more complicated. And so a group of people worked on this one. This was, I'm not going to actually go to this. This is just time-wise. This is the Colossus computer that Flowers created. There's paper tape there of German transmissions that just runs over and over again, and essentially all the hundreds of thousands of combinations of wheels in the Lorenz machine are then run against that paper tape over and over again. When they did it mechanically, it wasn't fast enough. When Flowers got this Colossus going, they finally got it fast enough. So they were able to know what Hitler was telling his generals through most of the rest of the war. Imagine this. Some of the information, they knew things were going to go badly, and they knew what the Germans were going to do, but they didn't let on because they didn't want the Germans to know they had figured out the coding system. Imagine having to make that decision. You know you could save a group of people, but if you do, then the Germans will change their coding system. But it did allow them, for D-Day, they were going across and they were going to land at Normandy. They got transmissions where Hitler said, I don't believe they're going to land at Normandy. I'm going to keep all my troops up around Calais, and I'm not going to let them go to Normandy, even if there are reports that people have landed. So the Allies actually knew that they had this breathing space to land and go inland and make beachhead. And they say that that shortened the war by 1 or 2 years, basically what they learned from this. Okay, after the war, one of the things about Alan Turing, he was an Olympic-class runner. He ran everywhere. He had some congenital issue with leg muscles, otherwise he would have been on the English Olympic marathon teams. But he lived 10 miles away from Bletchley Park, and he'd just run there every morning and back every evening. He left Bletchley after the war, went to the NPL laboratory in London, and took everything he'd learned, wrote a design for a programmable computer, and they started working on it. It became known as the Pilot Ace. Unfortunately, it took a long time. He got frustrated with how slowly this thing was going. Here's another picture of it. Max Newman is the final person you need to know about. He was an amazing mathematician. He ended up being a lecturer at Cambridge, and it was his 1935 lecture about Gödel's theorem that inspired Alan Turing to work on the paper. And when Newman got the paper from Turing, a draft, he realized how important it was, and he made sure it got published. He also got Turing to visit Princeton, where Turing was working with Alonzo Church and a bunch of other people who were there. And finally, Newman was invited to Bletchley Park. He was the one who was put in charge of mechanizing the decoding of the Tunney system, so he was in charge of that Colossus computer. He then went to the University of Manchester and started a mathematics department up there, and he decided that the mathematics department should create a programmable computer. And he took Turing's ideas and all the engineers from Bletchley Park and put together the computer that you can see in the bottom that is actually running right now at Manchester, and they called it the baby. Eventually, Turing, frustrated with the slow speed down in London, was invited by Newman to come to the University of Manchester and work with him. So here was the Museum of Science and Industry. There is the storage and the program of the computer. It's actually a CRT display with 64 dots. You program it and with the dots, and the data comes out on the dots. But it actually is a completely working programmable computer. I believe it's connected to the internet, and you can program it if you go looking for this. The successor was a company in Manchester called the Ferranti Computer Company. They created the Mark I. This is the only picture of Alan Turing at a computer. He started using computers. He started thinking about intelligence and what computers might become. And this is the paper that my AI class is very familiar with. In 1950, in the Mind journal, he wrote Computing, Machinery, and Intelligence, where he proposed his test called the imitation game. The idea, put a computer in one room, a person in another room, close the doors, have a questioner send questions to those two rooms. The computer tries to fool the questioner into thinking they're the person. The person tries to make sure that the questioner thinks they're the person. And he said, if the program fools 50% of the questioners, then we can consider it intelligent. So it's known as the Turing test. It's run every year as the Loebner competition. People said to him, that's a stupid definition of intelligence, and his response usually was, do you have a better one? And so this has become known as our test for intelligence. This is kind of interesting. At the same Science Museum in 1951, Turing actually saw this tortoise. It was one of the first, essentially, AI creatures. It basically has sensors that allow it to find out where the light is and go toward the light. So I'm gonna go past it, but you get the idea of it. And there's a picture of the actual thing. Okay, on to Professor Bernard Richards. This is a Chinese restaurant where we had dinner. I'm going to show a video I took at the Science Museum, which is, the video is bad, but the audio is the important thing, where he talks about working with Turing. Professor Richards did some amazing stuff himself. First co-author of a monograph on having a contraceptive pill. First database of infectious diseases. This guy was pretty impressive. He actually, if you've used a camera with a zoom lens, he wrote functions on how to calculate optical systems so that zoom lenses would work. Pretty amazing guy.
My name is Bernard Richards, and the honour of being able to work with Alan Turing